So I am Sebastien Preys. I've been working for Ondalis company for 10 years, and I would like today to share with you our experience on a specific domain related to multivariate data analysis, and especially about the PAT approach. So Mr. Brian mentioned it today before. So process analytical technology, and especially in the case with batches, so for batch modeling. And okay, I'm sure that some of you are aware of it, and some of you already implement this approach. So I hope a nice discussion will come afterwards. So Ondalis is a company which is located in Montpellier, France, and we provide services, consulting, and training for chemometrics, so multivariate data analysis. And you have some of the keywords here, so exploratory analysis, data mining, modeling, multi-block analysis, and then we deal with very different kinds of data, so spectroscopy, mass spectrometry, imaging, and so on. So today I would like to focus on this specific aspect, which is PAT. And for us, our experience comes really mostly from our clients from the pharmaceutical industry. And we see and we know that more and more people from the agro and food industry adopt this approach, and so it's quite interesting to see this phenomenon. So, what is first the PAT initiative? So, you have an example here to illustrate a process, classical process in the pharmaceutical industry. So you have here the inputs that we can call raw materials, and then different in-process products, and at the end, the final product or end product, which is characterized as well. So the specifications on these final products will give you, will allow the release of the product or not. And you have intermediate measurements, so on what we call the critical quality attributes, here, for example, here, the weight, for example. And when these attributes are identified, you have to control certain critical process parameters, so the CPP here, and with sometimes control loops. Okay, that's the general frame. And this is not a brand new idea, PAT. So historically, we talked about PAC, so process analytical chemistry, to supply quantitative and qualitative information about a chemical process, so in a wide sense, biological, chemical, physical, not only to monitor and control processes, but also to optimize its efficient use of energy, time, and raw materials. So this is a kind of monitoring and control of key processes, parameters, to provide the desired quality of the end product. Okay. Then we moved to the PAT with the now famous FDA initiative in 24. And this is a framework for innovative pharmaceutical development, manufacturing, and quality assurance. So I stress out on the three of these domains, okay? So this is a system for designing, analyzing, and controlling manufacturing through timely measurements. So this is mostly done in real time, of critical quality and performance attributes of raw, in-process, and end products, with the goal of ensuring final product quality. Okay, so this is the general definition. Actually, so we are in the risk and process session, and PAT is really a risk-based approach for different goals. Okay, so you have different levels of aims with this approach. And the first one is process understanding. Then you can use this approach to do optimization, and mostly continuous process optimization. And then improvement of the process robustness, especially during the development phase, using quality by design methodology. And I mean, the final goal is really to replace the classical quality control approach, which is done on the end product, so nowadays still, most of the time, and to replace this classical quality control approach by real-time release, or what we call the RTR in the pharmaceutical industry. And okay, it's not done yet, but this is the trend. For this PAT approach, so you can identify different tools. You have first the process analyzers, so the sensors. They can be, of course, online, very complex, like spectroscopy, but you have to really consider all other measurements that you do routinely, I mean, without new sensors, so online and offline maybe, so including all kinds of sensors. Then it includes the process control tools to monitor the state of a process, so by measuring the CQA and to manipulate the CPP to maintain a desired state, so with specific set points. And so, of course, you have the multivariate tools for design, data acquisition and analysis, so the 3 steps. So design of experiments and multivariate data analysis. So I will focus on, of course, on this step, I mean, on this tool. And then you don't have to forget the continuous improvement and knowledge management. So using all the IT infrastructure and also to manage all the regulatory papers and requirements. So let's go to the multivariate tools, so which is our main concern here for this conference. So Vold, in the paper, he proposed different levels concerning these multivariate tools for the PAT approach. So the first one, which is proposed, was the multivariate calibration that you all probably know on the CQA, which were identified, using rapid analytical measurements like near-infrared spectroscopy or Raman spectroscopy or whatever. So this is the first level of complexity. Then second level deals with the MSPC, so multivariate statistical process control. So this is really the extension of the classical SPC to the multivariate measurements. And by the way, just to be sure that we don't miss something, you probably, mostly of you know the difference between SPC and MSPC, but maybe it can recall some messages or arguments here. So these are 2 different control charts. So I will call them univariate control charts. So Scott has talked about it this morning, so I think it's quite classical here. You have, for example, the temperature, and here the pressure and the different control limits, and you have a series of measurements, observations for both variables. So here we are already in the multivariate case, so bivariate here, because it's easy to illustrate. And here you have some, most of the points are in control, and some of them are not, so out of control for one or for both variables, okay? So if you use 2 different univariate control charts independently, you can have, bad decisions. For example, if you consider this point, this is an abnormality. I mean, it's an obvious abnormality if you consider all the population of the samples, so the structure of correlation between the samples. And this abnormality is not detected in the univariate case, so with classical SPC control charts, when you have several variables for the same observations. You have also false alerts in the univariate case, which can be detected with multivariate control charts indeed. Okay, so just to go back to this second level, so the second level of PAT is really to implement multivariate statistical process control. The third level is what I will focus on in the second part of the presentation here, is the MSPC applied to the batches. So batch processes, when you have an additional way for the data, which is time, kinetics. And this is to decide if the trajectory of a batch is in control or out of control using multivariate measurements. And then you have two other steps that you can decline, such as multi-block analysis, if you want to combine different critical unit operations or steps in your process. And then at the end, but this is really ideal, just to implement a control procedure based on the models, the multivariate models that you developed. Okay. So let's focus now. So we will focus now on the BSPC. Just now. So in the BSPC case, you have this kind of data structure most of the time. As I told you, you get what we call a cube of data. So you have here the rows are for the batches. The columns are for the different variables, so the different process parameters that are measured timely, okay? And then you have the time dimension, so a 3 array of data to manage. And the process parameters, they can be whatever offline, online, pH, temperature, concentrations, and so on. Then most of the time you have additional data that we call ZID. For the same batches, you have a characterization of your raw materials, you have a characterization of your inputs, and you have even sometimes design of experiments or kind of design of experiments, okay? So this is what we call the initial conditions, and where you get all the set points and so on. And of course, at the end, you get the characterization of your end products. So this is the end quality, which they have to match your specifications, okay? So in most of the case, you get this kind of data structure, and the question is, how can I deal with this kind of data structure, and what are the questions that I want to answer to, what are the goals, and how can I exploit this kind of data? So there are several methodologies. The classical one is this one, so we can discuss about it afterwards, but it's not, maybe not the main point. But this is what we call the first step, the batch evolution modeling. So the main goal, the first goal, is to select the reference batches on which you will do your model, okay? Because if you want to do a model to monitor a process, you have to model it on the processes which are in control. So you have many different tools, many different plots or criteria to do it. The more intuitive and the easiest one is to use the initial variable trajectories as line plots. So, for example, this can be, I don't know, CO2 flow, okay. And then you define some limits, so easy limits to just to select your batches, so your reference batches. You can use then multivariate trajectories, so scores, for example, coming from your different process parameters, okay? And then you can be interested to just to plot the trajectory of the batches, okay? So you can do it in several ways. One way is to unfold the process variable matrix here, that way, and either do a PCA on it or do a PLS like this versus time, okay, or do a multi-way analysis, okay, whatever. What you are trying to see is really the whole trajectories of all your batches, and to the goal here is really to refine the selection of your batches, which will belong to the reference or to the training set. Okay. You can use also multivariate control charts, the T-square and the Q, so the residue charts for that task. Okay. Good. Okay, then the second step is called usually the batch level modeling. So you first want to check your batch selection, but this time you can unfold your cube of data in the other way. Okay, so batch-wise. So here you have all the remaining reference batches. So we went from here from 48 to 40, and then you can use as well the other matrix, the initial conditions, okay, using different ways, or multi-block analysis or whatever, and then just check on a score plot the similarities between the batches, and to check that you got your training set. Then the last step is to relate all these potentially explicative variables, so the initial conditions and all the process parameters, so the trajectories that you measured, timely, to your end quality. Okay, so for this you do symmetric regression model like PLS, for example, or multi-block PLS, and then you want to just to build a model, a predictive model on this. So you have a performance of your model. Okay, this is not the main point. And what is more interesting here is to use this model for some different goals. One of the goals is process monitoring. So Mr. Bryan talked about early warnings. This is a kind of early warning to anticipate the defaults, the faults in your process in real time. So you can develop such an interface for the operator, and then just to monitor in real time different multivariate control charts. So here the T-square or the SP, so the squared prediction error, so the residue, in fact. And then you have all the contributions to the of the variables to the model, also, or to the out of control point sample. So this is not a black box at all. And then you can have all your Y's here, so your end product quality parameters, which can be monitored and predicted in real time with, of course, large uncertainties at the beginning and less. So this is a kind of use of this kind of data structure of batches. But this is not the only one, and this is very important. When you have such a data structure, it can be interesting to have multi-level goals, and the first one is, of course, process understanding, just to investigate what's going on, and what is the influence of the parameters on my end quality products, what are the what is influence of the initial conditions or the design of experiments. You can do process optimization, and what I developed, you can do real-time process monitoring and fault diagnosis. So it seems to be very easy, but from data analysis point of view, there are still a lot of challenges. So I will give you a non-exhaustive list, so I mean we can discuss about it. And for each of these challenges, there are already many propositions, many tricks to overcome, but okay, we can improve this. So the first challenge is that most of the time, the duration of the batches is not the same. So you don't have an idle cube of data. So because of latency, lags, and so on. Then, of course, this is real data coming from R&D, pilot plants, production, and so you have a lot of missing data, of course. So how we deal with this. You have a lot of noise in this data, and you know you have offline measurements, online measurements. Offline measurements, they can be once a day for long, like bioreactors in pharmaceutical industry, and online measurements, they can be every minute. Okay, so then you have different frequencies of data acquisition. So you have to align your data and do resampling, interpolation, and so on. And you may need even more indices to explain your end quality of your product. So you may calculate process ratios or speed indices just to add some information that you didn't have in the trajectories of your process parameters. Okay, thank you for your attention, and now it's time, I think, for discussion. There is some time left.